So decision trees, we're talking about decision trees, and we tuned the model. How we learned how to tune the model using the depth of the tree as well as the number of nodes on the tree, number of nodes in the leaf tree. So using that, we tried to tune it, and we got a good performance on iris dataset. That's what we tried out. Now the question is, can I do the same thing for regression as well? I know that it works very well for the decision tree is working very well for normal data set. I mean, for classification, but does it work very well for regression as well? So in general, it the decision tree works very well for regression as well. Only thing is we need to understand how it is working. So let me give you an intuition about that, and we'll go into the problem. It's not much. It is a simple variation of what we do in the decision tree. So instead of calling it as decision tree, we call it as regression tree when we do regression on the on the data using decision tree. So let's say there is some data like this, and this data is about, let's say, the number of hits and age of the person. So it is more like this. So the age of the person, number of hits he did. If you remember the hitters data set, we used the hitters data set on logistic regression. So if you remember that data set, we have age of the person, number of hits he has done, and the salary of the person. The hits is nothing but it is the hits on of the baseball. How many hits he has done on the baseball matches. So last year, let's say he has done 50 hits. Based on that, his salary will be adjusted. So next year's salary, let's say it will be 5,000K per month, or or let's say 57K. And the age of person is, let's say, 24. Second person, he has a different age, 35 years, and he has 20 hits only, and his salary will be lesser. So let's say $35,000. So if you remember the hitters dataset, this is what we have done. Let me open the hitters dataset again. I'm just taking only two variables out of it. Yeah, hope you remember this dataset. Okay. Okay, the dataset itself is not there here, but at least you can see here. These are the columns. How many times he went to batting, how many hits he has done, how many home runs he has done, how many runs he has done. So maybe let's take, instead of hits, let me take the number of runs he has done in 1986. So based on 1986 performance, we want to predict what is his salary in 1987. So because his performance in 1986 is very important, and that is going to impact his performance in the, salary in the 1987. That's how we are trying to predict. So let's say, since it is runs, let's keep it as 550 runs, the first person. Second person has done, let's say, 350, something like 380 runs. Something like that we have the data for. Now, based on this data, I want to say his salary is, how much is his salary in 1987. So if you use runs, if you use decision tree, what happens is your data is divided according to some continuous variables. So these are all continuous variables. Age is a continuous variable, runs is a continuous variable. All these are continuous variables. It's okay even if you have categorical data, that's not a problem. But on continuous data, what we do during the split is we use a threshold split. That's what we have learned. And the same thing happens here also. So if you have age and runs plotted on the coordinate axis, and somehow let's say salary, I know that salary is a third dimension, probably you try to fit in the, let's say somehow you try to fit the salary also in this two-dimensional plane, maybe using a bubble chart. I hope you know the bubble chart. Bubble chart is something that can fit your third dimension into two-dimensional plane. How to do that? So age and number of runs you can plot. Based on that you get a point. So let's say this is your 24 years, this one, the first record, 24 years and 550 runs on the y-axis. But if I have to plot a third dimension, which is salary, how do you do that in two dimension? Generally you go for a bubble chart. So what does bubble chart do? Bubble chart has a simple bubbles, some round bubbles will be there. Now using this bubble, you can, let's say if you have larger bubble, you can say that the salary is more. If the radius of this bubble is more, you can say that the salary is more. If the radius is very, very small, you can easily say that his salary is less. So for now, I am keeping, this is a moderate salary, $50,000. So I'm keeping a moderate bubble. So age equal to 35. Number of runs he has done is 380, which is somewhere here. I plot another bubble here. This bubble will be smaller because 35,000 is less than 50,000. So comparatively smaller bubble I will draw. This is how I can plot three-dimensional data onto two-dimensional plane. Hope this is clear. Are you clear with the bubble chart, how to plot? This is called bubble chart. In fact, if there is any fourth dimension also, you can try to plot using a color of the bubble. But when you are using the color of the bubble, it means that you are using only categorical data. So the fourth dimension can only be categorical. Three dimensions can be continuous data. So that's how you can plot bubble chart. Are you clear with the bubble chart?
Yes.
I can show it in internet. Bubble chart. This is how bubbles will be there. So for example, consumer rating versus revenue. Each of these bubble is showing something. He is not clearly giving it. Yeah, the production cost. If you see here, the production cost is the size of the bubble. So what is your revenue? What is the consumer rating? How much it took for you to develop that product? The cost of the production. So the size of the bubble can be representing the third dimension. But here, if you see, there is a fourth dimension also, which is a product type. The fourth dimension we are showing using the color of the bubble. But thing is, color of the bubble can be only one of the 4 or 5 types or 10 types, whatever it is. It cannot be infinite number of types. So the color of the bubble can only be categorical. So that's why he chosen product type, product 1, product 2, product 3, product 4. The color of the bubble can represent only a categorical variable. The fourth variable can only be a categorical variable. You cannot plot 4 continuous variables on a single plot. Impossible. Is this clear? Same thing here also. He is giving the color of the bubble as different series 1, series 2, series 3, something. But he is not giving what is the size of the bubble, at least here. But at least here you will be able to understand. I think this is a better example. Yeah. Any questions on this? Okay.
No, sir.
So for now, instead of drawing all these bubbles, I'm drawing it as a simple cross. I'm just plotting it as a simple point. I can ideally I should be doing the bubble chart, but since it is easy for me to draw like this, I draw like this. Okay. Now I have plotted age based on age and runs. What is his salary? Assuming that this is a bubble. This is not a simple point. The cross represents a point. Just to make it visible to you, I am drawing it as a cross instead of a point. Now, based on age and runs, I want to predict his salary. Now, the thing is, if you see the data here, it's not a continuous line. It's not a straight line. It's something else. I can draw any. If you draw any regression will fit this linear regression. So it's not in the form that linear regression will readily accept actually. So what you should do? You can always go for decision tree whether or not there is a linear relationship. But of course, if there is a linear relationship like this, if the linear relationship is simply like this, always go for linear regression. But many times you will not find this kind of a simple relation. So if this kind of a simple relation doesn't exist, then you have to go for some kind of a tree-based model. One of them is the regression tree. So how regression tree will work? So earlier we already learned that regression decision tree just works by splitting the data on some column. The same thing applies here also. But the only thing is, if you go back to our original discussion of decision tree, when you do not split anything, one second. So when you start with an empty tree, what you're doing is you're taking a majority class. So when safe is 20 data points and risky is 15 data points, if you don't split further, what is the decision that you're taking? You're taking the decision of the majority class. That is because these are categorical data. In categorical data, the central tendency of the categorical data is mode. It's not mean, it's not median. It is mode. You remember that?
Yes, sir.
So we went with mode. We did not go with mean and median because it is a categorical data. So what we assumed is we go for majority class. And majority is nothing but mode. It's not mean, it's not median. Mode is nothing but the majority class or majority value in a category in a categorical data. So what we did is we went with mode. So in that case, let's say, giving that as an intuition, let's say if you split on age in regression trees, all these are salaries. These are no more categorical data. These are also no more categorical data. All these are continuous data. Now on continuous data, let's say I got a split here, age greater than 30. Age greater than 30 is my split. Let's say if I split the data on age greater than 30, what do I do? What should I predict when? So this is my decision tree now. Age greater than 30, greater than or equal to 30, let's say. On the left side, we have true. On the left side, it is true. On the right side, it is false. Now, age greater than 30 means how many data points are there? Let's say there is another data point here. 27. Number of runs is, let's say, 200, and his salary is $20,000. Okay. Now, if age is greater than or equal to 30, we have to go into this branch. Let's say I split it based on age greater than 30. So if age greater than 30, then we go into the left branch. Otherwise, we go into the right branch. Now, one second. Let me draw it in gray. Now, how many data points are there in age greater than 30? There is only one data point, this one, 35. So there is a one data point here. Let me call it as num data points. There is only one data point on the left side, and on the right side, number of data points is, how many are there to greater than sorry am I right? Yeah, I'm right. Sorry, I thought I am not wrong. So on the right side, age less than or equal less than 30, how many are there? Two data points are there where age is less than 30. So you write two data points. Now what to predict on this side, what to predict on this side? Any idea? Earlier what we did is we predicted using median. We predicted mode. We predicted using mode. When we do not split, mode is the prediction class. Similarly, when we do not split again here, let's say if we don't want to split again, what is the prediction that we want to do? Average. So there is only one data point, which is 35. So there is one data point, the average is going to be same, $35,000. On this side, what you should do is you should add up these two things and predict using average. What is the average? 50,000 plus 20,000 by 2, which is $35,000 again. So what we are doing in regression trees is we are doing the same thing, the same way. The whatever we have done, whatever we have learned is always still the same, but the only difference is instead of predicting the majority class, let's say if I don't split on fair, if I don't further split, what should I do? I should predict safe. Why did I predict safe? The majority class is safe. If I don't further split, I have to take the majority class. That's it. That's what I have done earlier in the decision tree. Now in regression tree, similarly, I keep on splitting, and in the leaf node, what I do is I predict the average of all the observations in that branch. Are you clear with this regression tree, how it works? Are you guys clear?
Yes, Sandeep.
Abid, are you also clear?
Yeah, Sandeep.
Okay. See, what we are doing is we in this case, what we did is we tried to use age as the splitting criteria and then tried to split. But what is the guarantee that age works very well, or number of runs will work very well? It might also happen that I should start with runs. And this is the same problem what we addressed earlier, if you remember. Feature split selection, how to select a feature or a variable. What we did, we have all these variables. We tried to split on each of these variables on credit. First we tried to split on credit, then we tried to split on term. Based on both of them, we tried to find out the misclassification error. Whichever is having the less misclassification error, that is the feature that I tried to split on. That's what I have done. Now here also same thing, except that, so let me write, the question is which feature to split on. How do I know that age is the better feature or number of runs is the better feature to start with out of these two variables? So what we can use is use SS residual. If you remember, SS residual is nothing but sigma y minus y hat whole square. We know this very well. What is the predicted value? Y hat. Y hat is the predicted value. The predicted value is coming from the average value from that particular branch. In this branch, the average value is 35,000. In this branch, the average is also 35,000. Maybe let's change the values a little. Maybe let me keep it as 40,000. So this will become 50 plus 40 by 2. 45,000. So the predicted value or y hat here is 45,000. And in this branch, the y hat is 35,000. So using these predicted values for whichever the data points that are coming here. So for example, let me write another column y hat. Y hat for this is 45,000. Y hat for this is, it is in this branch, 35,000. And y hat for this point is again 45,000 because it is in the right branch. So what happened? This is y. Now sigma y minus y hat means this minus this. Y minus y hat. I am not taking whole square for now. This is 5,000. This is 0. This is minus 5,000. That is about the y minus y hat. All I have to do is square up each of them, add all of them. Square and add. If I do that, I will get SS residual. So that is for age. Do the same thing for, try to find out the SS residual for even the number of runs. Now what you have to do is whichever SS residual, whichever variable has, whichever variable, or let me write properly. Choose the variable which has the best, or instead of saying best, minimum SS residual, and use it in the decision tree model. Okay, are you clear with this example? I mean, whatever I have done, I should not use what I should take is, I should try to split on age, try to find out the SS residual. I should try to split on number of runs, again try to find out the SS residual. Whichever variable is having the minimum SS residual, first choose that variable and try to build the model. Okay, it may not be age always, maybe if you try age and runs. So let's say, if example, let me give example. If we get sorry, on age SS residual equal to, let's say, 5000, on runs if SS residual is equal to, let's say, 3500, which one should you choose? If I did not calculate, I am just assuming these things. So if on age, after splitting on age, you got an overall SS residual as 5000. On runs, you got SS residual as 3500. Which one should you choose? Choose run, choose to split on runs as SS residual is minimum for that variable. Okay, same thing, remaining things are all same. So to build the tree, all you have to do is find out the variable which is having the best SS regression value, SS residual value. So whichever is having the best SS residual, use that SS residual, use that variable to split the decision tree. You keep on doing that until you have those stopping criteria. Let's say the maximum depth of the tree, or minimum number of nodes on the leaf node. Okay, if the SS residual doesn't increase anymore, all those stopping criteria, if you remember early stopping criteria, all those things apply here. Only difference is, instead of mode, you start using average. Instead of misclassification error or classification error, you start using SS residual. That is the only difference. Everything else is same. Are you clear with this regression trees?
Yes, Sandeep,
Yes,
this example, I understood this example very well.
You understood, right? So you keep
Yeah.
on splitting. What you do is, let's say age equal to age greater than 30, you split it. Let's say for age, you got the best SS residual. So you split it on age greater than 30. Now, again, you have to split on runs. Let's say on runs, let's say number of runs greater than 550, you have to split. What happens? So here there is no split. This is a pure node, right? Only one data point, pure node. You have to split on this one. So let's say number of runs greater than 550, or greater than 500 runs, less than or equal to 500 runs. Okay, this is one node, this is another node. How do you know that? How do you split here? You split using let's say number of runs is somewhere here, 500 is somewhere here. You split here only. Why you don't split here? On the left, I'm sorry, I split it wrong way. I should split this side. Greater than 30 is this side. So greater than 30, there is no need to split. I did not split it again. But less than 30, I split it again. Okay. Now what I should do? Greater than 30, sorry, this is 500, right? Greater than 500, I have to take another average. Less than 500, I have to take another average. You'll have another SS residual because the prediction here is changing. The prediction here is also changing. So take SS residual again. If the SS residual is good, then say you can go ahead and split on this number of runs. You keep on splitting your data continuously the same way. Only difference is, like I said, instead of instead of mode, use mean. Instead of classification error, use, what is that, SS residual or MS residual. Okay, let me call it as SS residual only, otherwise you will get confused. So squared residual, let me call it as SS residual. Okay, are you guys clear? I think this is the best way I can explain this one.
Yes, Sandeep.
Okay, any more questions?
No, I'm good, Sandeep.
Vijay, are you also clear?
Yes, Sandeep.
Okay. Okay. Now let's try to understand the same thing, the decision tree regression. One second, let me. Okay, I'm opening from your notes itself. Let me clear all the cells first of all. Okay. So the same thing, we can use some data set and try to understand how decision tree can be used for regression. So we can plot it like the way we plotted earlier. All those things we can do. Let's try to do that part today. I don't know, it is taking time. Yeah, let me load the data set and help you understand what is the data set. So this data set I have loaded from directly from sklearn. sklearn is our scikit-learn. Scikit-learn is our machine learning library where you can run any machine learning technique. So from sklearn.datasets, there is a datasets package in sklearn. So in that package, you'll find all the data sets that can be loaded without having a CSV file or Excel file from your local file system. It loads directly from the library itself. You don't have to give the file name, file path, all those things. So there are few data sets that are very important. So you can see breast cancer. Yesterday I was telling about breast cancer. That is already present in this data set. In this package. Diabetes data set is there. Digits, files. I don't know what are these. Iris is there. Yesterday I have shown you how to load the iris from a CSV file, but actually it looks like iris is already present here. So you don't have to go and download this original file. Similarly, there is a load wine. There is a wine data set which is also very famous. That data set also seems to be there. So you can load any of these data sets. In this case, I am loading Boston data set. Boston data set is nothing but Boston housing prices. Yesterday I was talking about it, but I did not complete the discussion. So Boston data set is nothing but it is about the housing prices of the Boston area. So I am loading the Boston dataset. Just call the load Boston dataset. You will get the dataset. In the dataset, once you load the dataset, generally what you have is, if you say dot, there is a data. There is a description, a full description about what is this data about. There is also the list of feature names. Feature names is nothing but variable names. Do not get confused with feature names. The terminologies might be different. Feature name is nothing but variable name. And finally, there is a target. Target variable is nothing but y. So in this case, Boston dataset dot target will give me the y variable. Dot data will give all the x variables. And the name of those variables is given by dot feature names. And if you want to read more about it, just print the description. That's how it is about the any of these datasets. Most of these datasets are organized like this only. So what I did, Boston dataset dot x, if I copy, then what happens is it will it will get me a list of x variables. But here I have only the numbers. I do not have the column labels. So for getting the column labels, I need the names. So I copied this Boston dataset dot feature names as names. So if I print the names, I'll get first column is crime, second column is zone, third column is some industry something. So only the column names are present, but it is very difficult for me to, because I know that this is crime, I am saying crime. But you may not get the same intuition like I get. Then how do I find out what is what? So to understand what column is about what particular data item, what you can do is you can print the description. Boston dataset dot description, like I said earlier. If you print the description, you'll get a nicely formatted description about what is this dataset about. So the header itself is saying it is a Boston housing prices, house prices dataset. It is all about housing prices. You can easily understand. And there are very detailed information, like say how many instances are there. Instances means number of sample data points or data points. Okay, or size of the sample. You can call it anything. So there are 506 data points. Each data point is having 13 numerical or categorical predictive variables. And finally, median variable, which is the attribute number 14, is usually the target. That's what he is giving. What is the target then? Target means y variable. When he says target means y variable. So here you can see median value of owner occupied houses in $1,000, thousands of dollars, is the y variable or the target variable. That's what he's saying. So the average value or the median value of the houses in $1,000. So let's say he gave 10 as the number. It means $10,000. If you see $20,000. That's how it is. So if you print this, so what he's giving 24. 24 means $24,000. 21.6 thousand dollars or $21,600 is $34,700. That's how you have to interpret. This is not $24. Okay, the house is not coming for $24. It's coming for $24,000. That's why he gave it as thousands in $1,000. So you have to multiply whatever you see there with 1,000. So what it is giving? So first variable is giving the crime rate in the town. Then we are getting how much is the proportion of residential land. Then the third one is giving proportion of non-retail businesses. That's why it is called Indus. Indus means industries. Is Charles River present or not nearby? If yes, 1, otherwise 0. Then nitric oxide concentration, how polluted the air is. Number of rooms, average number of rooms per each dwelling. Age of the uh, age of the owner occupied houses. Then distance to 5 different employment centers. So there are employment clusters. You have to find out the distance from each of them and do a weighted distance. Either you can do a average or something like that, or median or something like that. Then radial access to the highways. Then what is the property tax rate? How much is the property tax rate per $10,000 of property? And pupil to teacher ratio, which means how good is the what do you say? How good is the student community, or the schools and all? If the student pupil ratio is good, pupil teacher ratio is good, then it means that the teacher will have better concentration on the student. Otherwise, he may not have. And the percentage of black population, it's a little racist, I know that, but that's fine for now. So then the percentage of lower status population, this will give you, if people are if there are more people in lower poverty line, then it means that it is not a good area, or it may not increase your property rate in the near future, something like that. And the median value of this is the target value. That's how actually we have the data for. Are you clear about the data?
Yes, Sandeep.
Okay, so let's take a break now. I think this is a better time to take the break. Let's take the break and come back at 7:20. Yeah, 7:25 will come back. Actually, I have some things to look up. We'll come back at 7:25. Is that fine? Let's take 10 minutes today.
Sure, Sandeep.
Okay, then. We'll come back at 7:25. 25. Okay. Is everyone back?
Yes, Sandeep.
Okay. So again, we do the same kind of thing. So first we need to do a train test split, which means we have to divide the data set into train, validation, and test. But in this case, I am doing, or let me do both of them, no worries. So first let me do train and test split. Let me call it as test. So I have splitted my data into train and test. Now again, I am taking the train data set and splitting it again, like the way I split it earlier yesterday. X train, Y train, test size equal to 2.2, and I can give the random state, so that the idea of giving the random state is repeatability. The train and test split, what it will do is, this method will randomly pick some of the data and put it into test data set. But the problem is, next time if you run, you'll get a different data set. So to avoid that, you give some random state. If you give the random state, how many times you run, it will give you the same split, train and test data set. Train, X validation, Y train, Y validation. Sorry, this is train test split, not test split. Okay. So using these, I splitted train and test. First, I splitted data into train and test. Then I splitted train data into train and validation. Now, if I print the sizes, train data sets dot shape is giving me the size of the train data set. This is giving me the validation data set size. And finally, this is giving me the test data set size. Sorry. Okay. 320 in the train data set, 81 in the validation data set, and 102 in the test data set. That's how I'm splitting. Okay. Now that I splitted the data, what I'm doing is I'm doing the early stopping. I'm trying to see if the early stopping works in this this regression tree. So let me try to use, instead of early stopping, before that, maybe let's try to understand if the classification works properly or not. Sorry, regression works properly or not. So what I'm doing here, I'm running the decision tree regressor. Yesterday I did not use decision tree regressor. I used decision tree classifier. Decision tree classifier will classify the data. This one will try to do a regression. Again, you can give a random state so that it will be repeatable. So let me run the classifier using the training data set. I get a model. Using the model, I predict the validation data set and try to find out the mean square error on the validation data set. That's what I'm doing here. I think import is missing. 1 second. Yeah. Let me move this up. Running full decision tree regressor without early stopping. I'm running without any stopping criteria. Let me call it as 3. And this is 4. 5. 6. And 7. And that's how I'm trying to. So I'm trying to use the decision tree without any early stopping. So if I do not have any early stopping and try to predict the data on validation data set, I'm having a mean square error of 16. That's what I'm having right now. Okay, I'm not using any early stopping. I'm building the full tree. Now if I want to print this tree, let me print the tree from here. I'm printing the tree to file. It's taking a little time. It looks like it is a big tree. So you can see the tree is very, very big. Are you able to see this? It's very, very, very big. And that because of this problem, if the tree is too huge, the problem is you cannot, the data will be overfitted. That's what we have learned. If the tree is too big, the data will be overfitted. If there is an overfitting problem, then obviously it means that your tree is, your data is not proper. Your model is not proper. So what you should do, you should try to minimize this overfitting. You should not have this much of problem. You can see, this decision tree is it's very difficult to read also. I don't know if it is possible to read if I open it from your OneDrive. Yeah, this is your regression tree. I think it is unreadable. Okay, somewhat it is readable, yeah. But still, you can see how many nodes are there. The number of nodes are too many. So, but what it is saying is, the first node is saying I start my splitting from LSTAT. LSTAT is number of lower income group or lower income population in that area. So if LSTAT is less than 9%, then your MS residual is what it is trying to find out. So when you split on again LSTAT less than 16.91, you can see the MS residual got dropped from 81 to 22. Again you try to split again, it went down to 8. So your MS residual kept on decreasing for that branch. It went to 0 also. When it is 0, you don't have to split anymore. There is only one sample there. Okay. The value is saying the average value in that branch. So if you stop at this branch itself, the average value in this branch is 17.4. That's what you have to predict. So if you come down, so the value is saying there is only one sample, the value is $22,000, $22,800. This is $23,000. So when there is only one sample, you don't have to split again. So that is where this decision tree is ending. But the problem is the interpretation is very difficult. You can see how many splits are there. Okay. Are you clear with this? I did not use any early stopping. That's why it is becoming a very, very huge tree. It's not even small, simple tree anymore. Are you guys clear? Why it is overfitting?
Yes, Sandeep.
Okay. Anyway, you can clearly see the data is too huge. I mean, the decision tree is too huge, and it is very, very difficult to interpret, as well as it is overfitting by default. And I don't want to overfit. So I want to use some early stopping criteria. I don't want to use without early stopping. I don't want to use. So what I do, I'm trying to use early stopping with max depth. What does it mean? I'm giving the max depth column, my max depth field to the tuning parameter to the decision tree regressor, and I'm trying different depths. At each different depth, I try to I try to get the MS residual. So at some depth, my MS residual might be hopefully less. So that is what I'm supposed to do. So here again, if you go back to our original idea of doing this tuning, the idea is simple. Whenever I say tuning, you should come back to this graph. This is training error. This is test error. So all I want is the minimum point in this, or validation error in this case. Validation error. All I want is the minimum validation error. Once I get the minimum validation error, that is the model complexity I have to use. This x-axis is model complexity. And model complexity, in this case, I'm saying depth is my model complexity. So I'm changing my depth of the tree. Using the depth of the tree, I'm finding out the MS residual or errors. Based on the error, whichever depth is having the minimum error, that is the depth I am going to use. So in this case, again, what I did, I kept it in a function so that I can pass the depth automatically. Once I pass the depth, I got a classifier. For that classifier, I'm using the trained data set to fit the model, and I'm predicting the model using validation data set and calling this mean squared error. There is a function called mean squared error in sklearn.metrics. This sklearn.metrics is going to have all the metrics, different metrics, classification error, mean squared error, all those different types of errors you'll have here, metrics. So here I'm calling the metric called mean squared error on y, validation error of y, and the predictions, y minus y hat whole square, right? So this is y, this is y hat. So this guy is going to do y minus y hat whole square. That's what it is going to do. So I created a function, and I'm creating a list of depths. What are these depths? Depth equal to 1, depth equal to 2. What is the maximum depth that the tree can grow? That I'm giving it as list of depths. Depth equal to 1, 2, 3, 4 until 15 I give. Normally 15 means depth equal to 15 minutes means you'll get mad. The tree will be too deep, very complex. So let's say this is a tree. When depth equal to 15, the tree will be very, very complex. How much depth is it now? 1, 2, 3, 4. At depth equal to 4 itself, it is like this. You can imagine at depth equal to 15 how it will be. So, but that's okay. I'm trying to find out all the mean squared errors for each of these depths. So what I'm doing, I'm calling this fit decision tree with max depth by passing one of these depths from this list. For each of these depths, I'm calling this method. What I get is a list of mean squared errors. I'm keeping in a list of errors. If I do this and plot it in a plot, what I will get is a list of, I mean, some kind of a plot which will show me what is the best depth I can use. In this case, 8 looks like a reasonable value. At the same time, 4 also looks like 4 or 5. I think 5 is also reasonable, somewhat reasonable, competing. Again, according to Occam's razor, which one is better? Is 8 better or 4 or 5? 5 is better. Let me show you the errors. 1, 2, 3, 4, 5. 5 is saying 17. 6, 7, 8, 9. 9 is saying, or 8 is saying 16. 16.7 or 17.9. These are very close if you ask me. If you ask me, these two are very, very close. What I would suggest is go for this 17.9 first. If it is not working out, then only go for 16.7, which is depth equal to 8. Because of the principle of Occam's razor. What is it saying? Among competing hypotheses, the one with least complexity is complexity. Occam's razor will tell in a general fashion. It is not telling in. It's not telling only for trees.
Okay.
It's not only for trees. Where is it? I don't know. I missed it probably. No, it is in overfitting. Sorry. Yeah. Among competing hypotheses, the one with fewest assumptions should be selected. Fewest assumptions means simplest. Simplest model is what I should select first. If that is not working out, then I should go with the more complex one. So I would say depth equal to 5 is reasonably well. Depth equal to 8 is also doing well, but it is more complex. The difference between this one and this one is not much. Only 1 point is difference. For that, should I go with depth equal to 8 is what is my question. Maybe not. So the question is, for one difference of 1 in mean squared error, if you increase your depth from 5 to 8, it is not such a good model. That's what my intuition is saying. Okay. So these are very close. So I would say these two are competing hypotheses. Among them, the one with simplest hypothesis is what I should take, which is depth equal to 17. Depth equal to 5, which will give me an error of 17.9. Is that clear? Because from depth equal to 5 to 6, somehow it is increasing. We don't know why it is increasing. So these are all risky decisions. So always go with the simpler model. That's what Occam's razor I already explained, right? Based on Occam's razor, you can go with only 5. Do not go with 6. Okay. Are you clear with this?
Yes, Sandeep.
Similarly, I can do with the minimum number of samples instead of going with the depth. Or let me plot this first. First of all, let me plot this. Okay, I'm plotting it again. I don't know if it is CLF or not. So to use it as a CLF, what I should do? I am interested in depth equal to 5 only, nothing else, right? So I'm running this again. 17.92, the same thing that we got there. Now I'm going ahead and running this model. Much simpler, right? At least it is not as complicated or as bigger as the earlier tree. Okay, earlier tree it took a lot of time for me to plot also. If I remove this, what happened? For printing the tree itself to the file, It is taking a lot of time. This is much complicated. But when I try to make depth equal to 5, when I stopped at depth equal to 5, what happened? My tree is much simpler. It is printing much quicker also. Okay, much simpler. Are you clear? 1, 2, 3, 4, 5. 5 is the depth. That's how you can count the 5 depth equal to 5. You can open from the file itself, file also. Okay, that's how you can try to find out the depth equal to 5. Are you clear how it became simpler? Any questions?
Yeah, yes, I'm clear, Sandeep.
Okay, then I can do with min samples also. What is this min samples? Each node should have minimum number of samples. That's what I gave as another early stopping criteria, right? What are the early stopping criteria? Pruning is not possible anyway in Python. Minimum depth, limit the tree depth. That's what we have done now. There is another way to do the early stopping. Have a minimum node size. If the node size is less than that minimum, then do not split, right? So you can use the minimum split criteria also. So instead of passing the depth, I am passing minimum samples leaf, which means minimum samples to be in the leaf to be defined. So I am passing it as a parameter to this function and doing the same. The remaining things are same. All these things are same. Mean squared error, all those things are same. So I am running it again. For each of these minimum samples, what I am doing? Minimum sample, I am starting from 1 to 15. Each of it is going to give me a different tree. So I am passing this minimum samples to the function. If I pass this to the function and plot it, somewhere at 8, 1 and 2, 1 minimum sample 1, minimum sample 2 means it is overfitting. That's why the error is more. Then it came down slowly. At minimum sample 8, it is at the minimum. Again, if you see, actually you are supposed to get this kind of a curve, but you don't get it. You will never get it anyway. All you have to do is, the reason for telling this one is, it will start decreasing and at some point it will increase. That's what is the idea. What you should do is, you should find out a point where it is at the minimum point. That is the point you should use. So in this case, it went down, and at some point it got the minimum value and it started increasing. It may not be exactly you. That's why, if you remember, in our picture, there is something like this. You remember that picture? Hope you remember. I think you forgot. Let me open it. Performance assessment, when I was telling about it, you remember generalization error, all those things. Actually, I should use generalization error. In generalization error is supposed to be like this U curve. But I don't have generalization error. What I do is, I use a test error instead of generalization error, and it is like this. Somewhat approximation. It's not exactly like this. That's what I'm going to use. That's what I said. So that is the reason, because it is not generalization error, the true generalization error, you will not see the U curve properly. But still, using that U, you can try to find out what is the minimum point. So what is the minimum samples that you have to use? This one. Again, the competing hypothesis is this one and this one. Which one is simpler? In this case, the simpler model is the one which is having more number of minimum samples. Right? Here it is one sample. One sample means it is a very big tree. Yes or no? Are you clear?
Yes, Sandeep.
If you are having in the leaf node, if you are having only one sample, it means you have already splitted the tree too much. So if you consider these two are competing hypotheses, which one is winning? This one is winning this time. The one which is having many samples in the leaf node. Okay?
Yes, Sandeep.
Are you clear or just saying yes?
No, I'm clear, Sandeep.
Okay. Let me plot it also. Let's say minimum samples leaf. Minimum sample leaves equal to 1. What happens if minimum sample leaves equal to 1? Let's go down and try to plot it. If there is only one sample in the leaf, then you are splitting too much. Again, you can see it is taking a lot of time to plot. It implicitly means that it is a big tree, very big tree, right? When minimum sample equal to 1, it is a very big tree. Now what happens if minimum samples in the leaf is 8? Sorry, it is comparatively more. The mean squared error is comparatively more. Earlier it is only 16, little bit more. But let's see if it is solving our problem of very complex tree. Simplified tree is simplified or not? Much more simpler. Let me go back and show you. See, if I don't have to zoom in to see the node properly. Much more simpler actually. But if you see properly, the depth is not controlled. How much is the maximum depth here? 1, 2, 3, 4. I'm sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is the depth. Let me write that. Okay, 1, 2, 3, 4, 5, 6th node, 7, 8, 9. I have to go down by 9 nodes, only then I'll get to the leaf node. But it should be always the maximum path. If you go this direction, 1, 2, and 3. Do not say that this tree depth is 3. You should go as much deep as possible in this tree and then count the depth. The depth of the tree, this tree is 9. It's not 3. Okay. Any questions so far?
No, Sandeep.
Okay. I hope this is clear how to tune using different parameters. I showed you one parameter which is depth. Another parameter is min samples leaf. Both the parameters I am showing you how to find out the depth. Now another good thing about decision tree is you can also try to find out the feature importance. I'm not telling you how the feature importance can be predicted. But what is the feature importance is it will show you from the list of original features which features are important. It will just give you the percentage of importance. So out of all the features, which one is important? The last feature is very important. Last variable is important. Similarly, the second variable is not important at all. What you can do is you can drop that feature completely. So the most important features I think is this last feature, which is lstat. Lstat is the most important feature, most important variable. The second most important variable is maybe this one, which is saying P ratio, PT ratio, which is pupil to teacher ratio. That is also very important, it seems. So you can find out which variables are important, which variables are not important. You remember variable selection in regression? Do you remember variable selection? Are you there?
Yes, Sandeep.
Yes, Sandeep.
I'm asking, do you remember variable selection? In regression, we have done forward selection, backward elimination. We tried to find out which variable is important. Similarly, here also, we can try to find out which variable is important and discard whichever is not important. For example, zone is not important, it looks like. And whether he is nearer to any river or not, it is not important. Similarly, fourth one from the last, which is rad. I'm not sure what is this rad. What is this? Radial highways. Whether you are nearer to the highway or not, that feature is not important at all. Based on this decision tree, what you can do is you can find out which features are important, which are not, and you can only keep whatever is important and try to create a model. Okay, that's how you can try to find out the which one is important and which one is not. Are you guys clear?
Yes, Sandeep.
Yes, Sandeep.
Okay, that is about the regression trees. You can use the feature importance even for classification. I did not do that earlier in the uh, previous notebook, but you can still go ahead and use it. Not an issue. I used it here because there are too many variables. I wanted to see which variable is not important. That's why I used it. But you can use it for the previous decision tree Python scripts as well. It's not just for regression. Okay. Any questions?
No, Sandeep.
So you forgot about the feature selection in regression? You're not responding? No, none of you?
No, I remember when you said about the forward and the
Forward, backward elimination.
Yeah.
So same thing, but here there is no need for forward selection, backward elimination. What it will do is this feature importance, or how it is finding out is, it is trying to find out using which feature is giving the best reduction in the MS residual. It looks like LSTAT is giving the best reduction in the feature, what is it, MS residual, and after that PT ratio is giving the next best reduction in the uh, reduction in the MS residual. So that's how it is trying to find out the feature importance. Same thing, but in reality, this works. This will work very well compared to the regressions feature selection, because regressions feature selection is very much tied to the. It is called parametric model. I don't want to explain all those things, but in general, decision trees feature importance is much more powerful, even though it is much more simpler. Actually, the way it calculates is much more simpler, but this works very well in practice compared to that one. Okay, if you want to select, let's say, out of these 15 variables, what are the important variables? I would suggest this time go for feature importance of decision tree, or you can go for a combination of both of them. Try that one and this one, and try to remove the combination of both of them. Okay, anything is fine. Any questions?
No, Sandeep.
I'm good, Sandeep.
Okay, with this we are closing the decision tree topic. We are still not done with the tree based techniques. I'm just thinking, should I go with complete the tree based techniques, or should I introduce other topics? I have not still decided. I'll see if I have to go with random forests or some other technique. Okay, so that's all I have for today. So thanks everyone. We'll catch up tomorrow again. Bye.